Good afternoon, everyone. My name is Joselyn Zapata-Paulini, and today I have the pleasure to present you our paper entitled Performance Analysis of 10 Machine Learning Models in Lung Cancer Prediction, in which I am the corresponding author, together with my co-author, Michael Cabanillas-Carbonell. This paper will be published in the journal Electrical Engineering and Computer Science. The article is structured in 6 sections. In Section 1, Introductions, the problem of the case study in detail. Section 2, Bibliographic Review, describe the study related to this research. Section 3, Methodology, is divided into 2 parts. Description of the machine learning models and case study. Section 4, Results, presents the model training results. The last sections are discussion and conclusion. Introduction. Lung cancer is one of the leading causes of death in the world, with a high incidence and mortality rate. Smoking is the main risk factor, accounting for 18 to 19% of causes, despite the advance in the treatment survival rate remaining low, with only 20% of patients living longer than 5 years. This study seeks to identify the machine learning algorithm with the best performance to predict lung cancer, comparing several models such as Logistic Regression, Decision Tree, K-neighbors, Gaussian Naive Bayes, Multinomial Naive Bayes, Vector Classifier, Random forest, extreme gradient boosting, multilayer perceptor, and gradient boosting. The result, discussion, and conclusion on the performance of this model are present. Methodology. This study compares 10 machine learning algorithms for predicting lung cancer. It was divided into 2 parts: machine learning models. Logistic regression, useful for multivariate modeling binary outcomes, 0 and 1. Decision tree, classifies data by rules based on divide and rules strategy. K-neighbor, grow data by similarity, useful in ambiguous cases. Naive Bayes Gaussian probabilistic algorithm classifies using Bayes rules. Multinomial Naive Bayes, adapted for text processing, supports vector classifiers. Generic classifier optimizes classification. Random forest algorithm for classification and regress with multiple scientific application. Extreme gradient boosting combines decision trees to improve prediction. Multilayer perceptor, supervised neural networks use backpropagation. Gradient boosting, efficiency algorithm focus on accuracy and speed. Case study. Understanding the dataset. The data were obtained for Kaggle with 309 patient records between 21 and 87 years old. men and women. The dataset obtained 14 attributes, such as age, gender, smoking habit, asphyxiation, fatigue, cold, cheek pain, among others. The key attribute is the presence or absence of lung cancer categories as positive 1 or negative 0. 2. Preparation of the dataset. Data were analyzed, eliminated duplicates, and transforming categorical variables into binary values 1 equals yes, 0 equals no. Variables such as gender and lung cancer were transformed into numerical data to facilitate processing. The absence of null data was validated, ensuring the quality of the dataset for training the machine learning models. 3. Exploratory data analysis. Diagnostic imbalance. An imbalance was observed in the lung cancer column, with more positive than negative cases. Risk factors. People who consume alcohol and smoke are more likely to develop lung cancer. 76 versus 3. However, some non-smokers and non-alcohol consumers also developed the disease. 38 cases. Primary symptoms: cough and chest pain are more common in lung cancer patients, while fatigue and shortness of breath are more frequent, although present in both groups. Secondary symptoms: anxiety and chronic illness have a slight association with lung cancer and may be additional indicators. 4. Data processing and modeling. Random oversampler technique was used to balance the data. Then, the dataset was divided into two parts, training and testing, applying scaling before training the models. Results: 10 machine learning models were trained using a Kaggle dataset. Best models support Vector Classifier, Random Forest, Multilayer Perceptron, Gradient Boosting. Achieved the best metric: 98% accuracy, sensitivity, and precision. Logistic Regression and XGBoost achieved 97% accuracy and precision. Model with lower percent decision tree. 94% accuracy. Gaussian Naive Bayes. 92% accuracy. Multinomial Naive Bayes. 81% accuracy. Visual comparison. Figure 6 shows the accuracy comparison between all models, highlighting the superiority of SBC, RF, MLP, and GB. Discussion. The study evaluated multiple machine learning models for lung cancer prediction, highlighting that SBC, RF, MLP, MGB achieved the best result, reaching 98% in accuracy, precision, and sensitivity. This model outperformed or matched previous studies, although their performance is highly depends on the quality of the dataset. The results suggest that the proposed methods of the diversity of the data contributed significantly to the high result obtained. It is recommended to use more diverse datasets and explore hybrid models such as neural network to improve accuracy and clinical utility in early cancer detection. Conclusion: the Support Vector Classifier, Random Forest, Multilayer Perceptron, and Gradient Boosting models stand out with the best result in precision, accuracy, and sensitivity for lung cancer prediction, showing promise for early detection. Also, alcohol consumption, smoking, and symptoms such as cold and chest pain were identified as key factors. For future research, it is suggested to test natural networks and explore large and more diverse datasets to improve the accuracy and generalization of the models. Thank you for your attention.